Okay, so welcome everyone to this week's One World Property Seminar. Before I introduce this week's speakers, I just wanted to give an announcement for next week. We have Cristina Toninelli and Fabio Martinelli. So please join us for that. But this week we're really pleased to have Lorenzo Zambotti from Sorbonne, who's going to be speaking about sorry, just a second, I've forgotten the talk name. Some stochastic PDEs for the future. So thank you.
Thanks a lot. Let me try to share the screen. Is that okay?
Yeah, that's great.
Okay. Thanks a lot. Thanks to the organizers and thanks to everyone for being here today. So this is the talk of my title, some stochastic PDs for the future. And after my talk, so Francesco will speak about the reconstruction theorem without regularity structures. Okay, so let's see. Let's start. Okay. These are the kind of stochastic PDs that I want to discuss today. They are quite classical. So it is a parabolic PD plus some nonlinearity plus some noise. Here you will see, so U is a say random function or in general a random distribution. Anyway, an object U which depends on two explicit parameters, which are time and space, and also depend on randomness. Then you have F, which is a coefficient, in general nonlinearity, so it's supposed to be a deterministic, for the moment, a smooth function. And psi is a space-time white noise. What is this? So it is a centered Gaussian field on space-time, such that so the covariance function is written here. So you have to think of again a random function which depends on space-time, such that it gives independent values to different space-time points. Okay, maybe so you can be a bit say puzzled by this expression here, which is of course say distributional, but you can realize easily this space-time white noise in the following way. You can write psi of Tx as a series of zeta k times ek of Tx, where zeta k is an IID sequence of standard normal random variables, and ek an orthonormal system in, again, L2 of space-time with respect to Lebesgue measure. Note that, so almost surely psi is not a function, but a distribution. So it's a very, very regular object, but it is well defined as a distribution. Now, let me go back to the equation. I consider the linear case. Actually, well, it's not really linear in a sense, it's an affine equation, but anyway, I mean that there is no linear term. F is 0 here. Now, in this case, this random field, okay, sorry, I consider d equal to 1. So this is true in general for any d, that the random field is Gaussian and explicit. But for d equal to 1, there is a very special property that the function, so this is indeed almost surely a function, and it is even continuous as a function of Tx. So more precisely, U almost surely is almost 1/4 Hölder in time and almost 1/2 Hölder in space, but not better. Okay, and so you recognize, so 1/2 is the parameter, Hölder parameter of Brownian motion. So indeed, the function is essentially Brownian in space and okay, a bit worse in time. Okay, so this will be very important later. In one space dimension, these stochastic PDs driven by space-time white noise are almost surely continuous functions. If I consider the case of d greater than 1, some space variable in 2 dimensions or higher, so again, the random field is Gaussian and explicit, but the function is not a function. The solution is a distribution. And the higher d, the worse the irregularity of U. Okay, and this has a very important consequence. In dimension greater than 1, non-linearities of U are in general ill-defined, or anyway, they are not easily defined. Now, let me discuss some physical models. So you have probably already seen them. So the first is the celebrated KPZ equation, Kardar-Parisi-Zhang, where you are in one space dimension. So you have, again, the parabolic term, the space-time white noise, and the nonlinearity depends on the gradient in space, and it is the square of the partial derivative with respect to x. Now here, since I said before that U is okay, sorry, now I've moved from the linear to the nonlinear equation. So of course, U is not the same anymore, but still we believe that the solution to the nonlinear equations are similar to the solution of the linear equation. So the nonlinear equation is supposed to be a perturbation of the linear one. So the typical properties of the solution to the linear equation should still be true, more or less, for the nonlinear one. At least the bad properties should only become worse in general. So in particular, this aspect of Brownian behavior in space here it will be conserved. So we said that U was at most 1/2 minus kappa Hölder in space, and therefore the partial derivative with respect to x is not a function; it's only a distribution, and therefore the square is ill-defined. Okay, so for this reason, so this equation was defined in the 80s by these theoretical physicists, and then from the mathematical point of view, it remained a mystery for almost 30 years. Here, I'm not speaking about all the activity related to particle systems, which was initiated actually 10 years after the original paper by Bertini Giacomin, and because they used a trick and they linearized the equation. So in some sense, they did not really work on the equation as it is written here. I am here interested in the at least say problem of well-posedness of the equation as it is written here on the slides. Okay, so this was solved in 2012 by Martin Heyer. And the second equation is the stochastic quantization in 3 dimensions, which is okay, written like that. So again, this was written by physicists, so Parisi and Wu, and then later by Ionel and Mitter. There were the first mathematical results, but it was a modified version. So this is the version which is nowadays most popular. And you see that here U is itself a distribution because we are in dimension, space dimension higher than 1, and therefore the cube is ill-defined. Okay. So more generally, you can introduce a class, not any choice of capital F, but a class of equations with this kind of form. Even if you have only polynomial nonlinearities, as soon as you encounter in your equation a product of some distributions in the sense of generalized functions, then the equation is defined. So it's not just a problem of well-posedness, it's a problem of definition of a solution. You really do not know naively how to say that an object can solve the equation. So in fact, indeed, so this was at the origin of the theory of regularity structures, which will be so the topic more of Francesco's talk, although the title is Without Regularity Structures. But still, I want to say, I have 2 slides on this, and there is something I want to say which is interesting for the rest of my talk. So here, one of the insights that allow to solve this equation was that it is very important to study, to reconsider the map from the noise to the solution. So the map which from Xi associates U in this equation. So indeed, Martin's regularity structures, like Terry Lyon's rough paths in the case of STEs, in some sense separate analysis from probability. So suppose you have a solution. In general, this is a measurable map. So U is a function of Xi. It is a measurable function of Xi. And you split this map in 2 different maps. So you introduce an intermediate object, which I call here X. And then you have 2 maps. So one which associates to Xi the noise X. And the second map, which is called phi, which to X associates phi of X, which I call U. Okay? So here, X will belong to a space M, which is a metric space, and therefore, well, the minimal here requirement will be that the map from Xi to X is measurable. And then phi, which I call the solution map, is defined on this space M with values in distributions, so the natural space where U is supposed to live. And there is an additional property that this phi is continuous. So I have, I said, a metric on M. I have a topology on distributions. I require that this map be continuous. Now, I have so an image. You see here you have Xi, which is a distribution. Here you have U, which is a distribution. This map from Xi to U, in general, is not continuous. It is only measurable. This is true for SPDs. It is true for SDs. And then the same picture would be relevant for rough paths. And I have this big mysterious space M. I have this phi, which is continuous, and I have this choice from Xi to X, which is only measurable. Okay, and this diagram commutes in the sense that U is equal to phi of X, where X is associated to Xi. Now, what is going on here? So, okay, let me go to the next slide. So, since they separate analysis from probability, regularity structures tolerate a very irregular noise, but they do not take advantage of many of the properties of noise. So here, in a sense, what I'm saying, and okay, of course, details may be more complicated, more delicate, but in general, in the setting of rough paths and regulated structures, the noise is your enemy. So it is what creates you the worst problems, and so in a sense you try to limit its action as much as possible. So I go back here. The noise appears only in this choice of this dot, so this element capital X, and the rest is completely deterministic. So maybe I did not stress this enough. Phi is really just a deterministic map from a metric space to distributions. All the randomness appears in the map from psi to X. Okay, but since phi is defined on a big space, it is not really using many properties of the noise which are encapsulated in X. Okay, so in some sense, if you want to study almost sure properties, which is what we usually do in probability, this approach has some weakness. Okay, so this is a complicated maybe topic which would require more better explanations, but I will come back to this point at the end to make a comparison with what I want to tell you now in the rest of the talk. So again, the message is in this context, you have a theory which works for a kind of generic class, and therefore you do not take advantage of, for example, the regularizing properties of the noise. Okay. Okay. Now I have invested a lot of energy in this theory recently, but in fact I come from a somewhat different place and perspective. So for example, so almost 20 years now ago, when I defended my PhD thesis, my vision of SPDs was very different. So I wanted to build the equivalent of the classical stochastic calculus, but in the context of SPDs. Okay? So my dream was to unify two different words. So I have I'm showing you now the covers of two books. So one is the first monograph on stochastic PDs, which was written by Daprata and Zabchik. So Daprata was my advisor, and therefore, so I knew him and his work very well at the time. And on the other hand, so this book, Reviews Your, which I started to read during my PhD, and which was quite, in a sense, quite far from my culture at the time, and which fascinated me enormously because it was so rich of surprising results. So, of course, I did not understand much at the time, but it was very, very, very inspiring. So, okay, I will explain you in the next slides why this project of unify these two words actually was somewhat doomed. So that indeed I think I somewhat failed. But okay, I did something. So I'm going to show this. So my lecture notes from the probability school in Saint-Flour in 2015. So it is, okay, somewhat insignificant with respect to the two previous publications, but still this is what at least a part of what I managed to do. And therefore, if you are somewhat interested in this kind of questions, you may find some good reading here. Okay, so what was my aim at the time? from now on, I will discuss only SPDs in dimension 1. So because the continuity of the solutions with respect to space-time is absolutely crucial for the rest of my talk. So again, the solutions to the linear equation are almost surely continuous, and the same is true for the solutions of nonlinear equations, at least with a reasonable coefficient f. So, for example, the standard theory requires f to be Lipschitz for well-posedness. Okay. Again, so since u is continuous, I can fix x, the space variable, and look at the time. So the process parameterized only by time. This becomes a one-dimensional process. So you might. So this is what I thought at the time. So maybe I can build some stochastic calculus for this process. So unfortunately, this is not Markov, simply because the process depends on the values for other points in space. And it's not a semi-martingale either. So maybe I can go back. If you, even for the linear equation, this is quite clear. So this would be the decomposition in, so martingale plus bounded variation part, but it is very simple to see that if you fix x, the martingale part has infinite. So the candidate martingale part has infinite quadratic variation, and this term is not a bounded variation. So this is certainly not a semi-martingale, and indeed, so it is possible to write. I wrote Anito formula, even so more than one for the map. So for the now you compute a nonlinear function phi of your process UTX. Again, so if u was a semi-martingale in T, you would be able to compute a Anito formula for that if phi is smooth. So I wrote a paper on this so more than 15 years ago, and recently, so Carlo Bellingeri wrote also an Ito formula for this kind of processes using rather the theory of rough paths. So, however, so it turns out that these formulae are not, how can I say? So do not have the magic of the one-dimensional or the say finite-dimensional Ito formula. It is very difficult to use them to do the kind of computations that we do in for semi-martingale. So okay, this does not mean that this is impossible. So maybe someone in the future will build on this and manage to use this Ito formula. But for the moment, this has not been the case. Okay, now let me go back. So let me talk for 1 second about SDs. So I consider again a Lipschitz coefficient, and I consider this SD. So I'm sorry, I put this non-aesthetical square root of 2. Why? Because now B is a standard Brennan motion. Now I am interested in the stationary measures of these equations. If I don't put the square root of 2 here, I have to put a 2 here in front of a capital F, and I didn't want to do that. So I prefer this, and I will not mention the square root of 2 anymore. Now, what is capital F? It is the primitive, one primitive of the coefficient small f. Okay, so this is well known in one dimension. In fact, for SPDs, there is a similar phenomenon. So if you consider this SPD, Okay, now I take actually instead of R, I take just the interval 0, 1 for simplicity. And I consider Dirichlet boundary conditions, homogeneous Dirichlet boundary conditions on 0 and 1. And then this SPD, so the solution, has the following stationary measure. You see, it is somewhat similar to the previous formula. There you had f of x. Now here you have an integral from 0 to 1 of f of phi of x dx. So phi is the profile in space of my stationary measure, and mu is the law of the Brennan bridge on 0, 1. So in particular, if f is 0, mu is the invariant measure of the solution to the linear equation. Here I assume that the measure is normalizable, which I did not assume for the SDE, but okay, this is just a detail. Okay, what is interesting here? So the SPD and the SDE, I wrote SPE, but it is the SDE, are well posed under some assumptions on F. Okay, so you cannot. Okay, this is exactly somewhat what I want to discuss later, but at least in general, one considers, say, Lipschitz. However, the invariant measures do not have an explicit dependence on small f. So you only see capital F here, okay, which is the primitive. So it is always smoother than small f. So in fact, the invariant measures make sense for a larger class of capital F. Okay, and now I want to discuss an example where this becomes interesting. Okay, let us consider this SDE in R again. So you fix alpha in 0, 1, and you write this equation. Now, the nonlinearity is replaced by this beta, which is this explicit coefficient times LT, where L is the local time of x at 0. So it is defined as this limit when epsilon goes to 0, which I can interpret as the integral from 0 to t of a function which is not a function, it is a measure. In fact, it's a distribution, the Dirac mass at 0, computed along the trajectory and then integrated from 0 to t. Okay, so this is called the Skew Brownian motion. It was introduced in the book by Ito McKean. It was later studied by Walsh because it had interesting probabilistic properties. And then this SD was shown to satisfy pathwise uniqueness and existence of strong solutions by Harrison and Shep, who used stochastic calculus. So it is a paper in Annals of Probability in 81. It is 5 pages longer, so I think this is impossible nowadays to write a paper with an interesting result, which is so short. No, maybe not impossible, but it's very rare. And what is interesting here, you see that the nonlinearity here is not Lipschitz, it's a distribution, but still you can prove that you have a uniqueness. So here the difficult result is mainly this pathwise uniqueness, okay, which is a strong form of uniqueness. So, and they really use, say, non-trivial stochastic calculus. It is not just that they take two solutions, they take the difference and prove that this is 0. It is more complicated than that. It is based on the Ito formula and with clever transformations of the solution. Another result that Harrison Shep proved in the same paper is that there is no solution if beta is greater than 1 in absolute value. So you see here, if alpha is in 0, 1 and beta is defined like that, then beta is less or equal to 1 in absolute value. But if you put here another beta, which is say 5 or minus 7, there is no solution. Okay. Now, in fact, let me give another construction. So you pick a Brownian motion W and an IID sequence eta k, independent of W, which take values 1 and -1. So 1 with probability alpha and -1 with probability 1 minus alpha. Okay, so the same alpha which was fixed here. Then you enumerate the excursions from 0 of the absolute value of W. And then you define X in such a way that the absolute value of X is the same as the absolute value of W, but so the sign of each excursion is decided according to the coin you're tossing with eta k. Okay, so each excursion will be positive with probability alpha and negative with probability 1 minus alpha. Okay? And then one of the results of the authors I mentioned is that the resulting process is the skew Brownian motions with parameter alpha. So it is a solution to that SDE. So I hope this is clear. It is like Brownian motion, but you are changing the probability of being a positive or negative of each excursion. So of course, for alpha equal to 1/2, this is again Brownian motion. For alpha equal to 1, this is reflecting Brownian motion, so everything is positive. And for alpha equal to 0, it is minus reflecting Brownian motion. Now one can explicitly compute the transition semigroup and show that this measure, so alpha on the real positive values and 1 minus alpha on the real negative values, is an invariant measure for the process, unique up to a multiplicative constant. So it is intuitive. Again, you see you have the alpha, which is the probability of being positive for the excursions, and the 1 minus alpha, which is the probability of being negative for the excursions. So this gives an invariant measure. So, sorry, if I go back, so is it possible to fit this into this framework of small f and capital F? In fact, if I set capital C, which is 1 minus alpha, small c, which is this log of alpha 1 minus alpha, f, capital F, which is C times the identity of the indicator function of 0 infinity, then indeed this measure m alpha is equal to C times the exponential of f of x dx. Okay, so I can rewrite the invariant measure in the context of the exponential of capital F. But we have seen that the SDE is more or less formally written in this way. So here, small f, maybe I didn't write it, but so small f is 2 alpha minus 1 times Dirac mass at 0, while so the derivative of capital F is C times Dirac mass at 0. So the constants do not match, okay? So 2 alpha minus 1 is strictly between 1 minus 1 and 1, while the log of alpha over 1 minus alpha can be any value in R. And so here there is something strange. We can put this in that framework, and at the same time we cannot. So how is that? By the way, you remember that Harrison and Shep proved that if you put here a constant which is greater than 1 in absolute value, there is no solution. So in a sense, you cannot hope to have a C here generic. So while you can put a generic C in the exponential. So again, why is there this strange phenomenon? So I am repeating this here. So the intuitive rule, small f equal to capital F derivative, where small f is the drift and f is the potential in the invariant measure, is correct if capital F is smooth, but not in general. So in fact, the point is that the drift of the equation, so small f, is not defined by the property of being the derivative of f prime, but it is defined by the property of the integration by parts formula that I have written here. So in the smooth case, here I meant that f is smooth. You have this, and the fact that f prime appears here determines, in fact, the generator and then the drift, which is equal to f prime. But in the case of the measure we have written, in fact, so the measure is constant outside zero, and there is a jump at zero in the density. Okay, and this jump at zero produces this Dirac mass, and you see the 2 alpha minus 1 appearing. So this is the right hand side of your integration by parts formula with respect to the invariant measure is what determines the drift of the equation. Okay, here I am repeating that beta is and this highlights the crucial role of integration by parts formula in stochastic analysis. This is something I have worked on a lot, and which it has an interesting content also for the rest. Okay, so let me continue. Again, so the Skew-Brennan motion was solved by Harrison Shep using stochastic calculus. Okay, so in a paper with another PhD student of mine, so Bunebash, in 2014, we introduced the SPD whose invariant measure is this. Okay, so again, I am using this capital F, which is C times the indicator function of R plus, okay, we proved that we had at least a weak solution satisfying this SPD. Now this time there is not anymore the problem of 2 alpha minus 1, etc. There is the true constant C which appears in front of the Dirac mass. But without stochastic calculus, we had neither pathways uniqueness nor existence of a strong solution. So Dirichlet forms give weak solutions, Markov property plus other results. They come with a replacement of stochastic calculus, but okay, there are advantages and disadvantages, again, especially no way to prove unique pathways uniqueness. Now, in a recent paper of 2 months ago, Siva Threya, Oleg Budkovsky, Koale, and Leonid Mitnik proved that this SPD in one space dimension is well posed if F belongs to a certain base of space of distributions. In particular, this covers the Skew stochastic heat equation, which I had introduced in that paper. Okay, so this for me is really a great achievement, a great progress. I have to say that my paper with Bunebash has been completely ignored. So it has been quoted only once since then. Even I have never quoted it. So I'm very happy that this question now has an interesting answer. So this makes me think that maybe also the question was interesting, and but the techniques are very, very, very new to me, at least. But I think they are new in general. So the authors use a new method to estimate the term which appears in the integrating form of the equation. So this is the additive functional. Once again, you see that continuity of U is important because you want to fix here X. And this is based on a tool which is called the stochastic semi-lemma, which is due to Le, one of the 4 authors. Sorry, here I forgot the accent on the E. Okay, so Francesco will say something about the deterministic semi-lemma, and I'm also going to say a few words, at least, of comment. So the semi-lemma is at the core of rough paths. It has been one of the results which have been generalized in regularity structures, and it is called the reconstruction theorem. But these are essentially deterministic results. So they form a part of the construction of that big map of capital Phi, which was not random. Okay, while this is a stochastic Sturm lemma, it mixes randomness and analysis, and which seems to be something that has to be done here. So if now I go back to what I was saying before, you do not expect to have say a generic result which says in a certain class of noises you will have a uniqueness of this equation. So this will be true almost surely with respect to the space-time wet noise. Maybe you can take fractional noises, etc. But you are really using the strong properties of your Gaussian non-degenerate noise here. Okay, I have some comment at the end on this. So again, the Skew stochastic heat equation now is known to have a pathwise uniqueness, and even that's true for a more general class of distributional nonlinearities, at least which belong to a certain space. Now, in fact, the Skew stochastic heat equation was a kind of a toy model of a more complicated equation on which I also worked for a long time. So my problem was, can we find a SPDE? So we said before that with the linear SPDE has the Brownian bridge essentially if you put boundary conditions as invariant measure. But now, can I find a nonlinear SPDE whose invariant measure is reflecting Brownian motion? Okay. Now it took maybe more than 15 years, but so recently with another PhD student, so previous PhD student, Henri Elad Altman, we finally understood, again using integration by parts formula, the form of this SPDE. Okay, so this is the one of the possible formulations on that. So the drift is so much worse than a derivative, a Dirac delta. It is the second derivative of a Dirac delta. Okay, so it's even more irregular than the Dirac delta. And okay, one of the motivations for this was that this should be the scaling limit of dynamical critical wetting models. Okay, I had to choose. I do not have time to explain what this means. So there are a few people who have worked on this question. So Giacomin for the static wetting model, so critical wetting models, but then Deutschel, Orenstein, Grothaus. So a few people have tried to work on this very difficult problem. And in fact, with Henri, we wrote so a more general class of SPDs, which have so distribution nonlinearities, which are critical in some sense. That means that they are quite hard, and in fact, for the moment, even the techniques of this recent paper do not cover this equation. But the fact that there has been a progress on the Skew stochastic heat equation gives hope for the future, of course. Again, so this is one of the PDEs, stochastic PDEs for the future that I wanted to show you. And as I expected, I don't have time to tell you more. So now I have some concluding remarks to summarize. So regularization by noise for SDEs is a phenomenon which has been known since the 70s, work of Zvonkin and Feretennikov. So if you have a nilpost ODE, if you add noise, then the corresponding SDE can be well posed. Okay, maybe that's not always true, but it is true in many examples which are known. So this is an effect of the noise, and this can work even if the drift of the SDE is a distribution. So again, maybe it's not true in absolute generality, but there are examples. But these results are all based on stochastic calculus, and unfortunately, as I discovered by myself, this is generally unavailable for SPDs with a space-time white noise. So my original project was maybe too naive. 20 years later, I can accept this. On the other hand, an important progress has come from this paper, which managed to prove regularization by noise for a class of such SPDs with distributional drift. But one of the main techniques is this stochastic lemma. Okay, and again, as I said before, so regularity structures, in a sense, separate analysis from probability, while tools like the stochastic lemma do not. So they really mix the properties of the noise and the analytical properties, but in a new way. It's not just standard PD techniques. This will give you, in this case, not what you want. Now, a kind of slogan. So regularity structures are used to solve equations with distributional solutions and continuous coefficients. But here we have rather discussed equations with continuous solution and distributional coefficients. So you really have two different settings. And in this context, one needs to use fine properties of the noise and of the solutions to the equation, and at the same time try so find the novel analytical techniques which are adapted to the problem. So this is a very interesting challenge for the future, I think, to continue to investigate interplay between probability, so irregularity of the noise, and analytical properties like singularities of the nonlinearities and so on. Okay, I stop here. Thanks a lot.
Thank you very much. So I'll just invite everybody to unmute yourselves so that we can thank Lorenzo. And if people have any questions, if you could either put them in the chat, or if you raise your hand, I'll invite you to ask your question. We have one question in the chat already. It's maybe been partially answered, but I'll ask it anyway, which is, in the second last slide, you mentioned sort of needed to be Bessel SPDEs, and the question was, why Bessel?
Yeah, so there are two reasons. One is that indeed, so the invariant measure is supposed to be a Bessel process, and here the reflective invariant motion corresponds to a Bessel process with the dimension 1, but we have a form of the equation for any dimension of the Bessel process. And okay, another reason is that there is an analogy, so with Bessel processes in the form of the equation. Okay, I was planning to maybe talk about that, but I didn't have much time. Actually, if you want, also Bessel processes have SDEs with distributional nonlinearities, at least in low dimensions. So between 0 and 1. Okay, probably I should have prepared a slide on that. But between dimension 0 and 1, a Bessel process satisfies an equation which is can be interpreted in the setting I have discussed, and for which I think there is no direct theory of existence and uniqueness. Again, one can use stochastic calculus and have the result, but there is no direct approach, which is somewhat unsatisfactory.
Okay, thank you. We have Carlo has his hand raised. If you'd like to unmute yourself and ask your question, please.
Okay. Thank you, Lorenzo, for your nice talk. I have just a question. You mentioned a result on the Skew Brownian motion and his representation in terms of Brownian excursion. Have you ever thought about like maybe similar result in this SPD's context, maybe to represent using like the excursion of the free field? I mean, of the free evolution. So it was just a suggestion and a question.
Yeah. Yes. Thanks, Carlo. Yes, this was part of my dream to write such, for example, excursion theory. But no, I've never really managed to do that. It does not seem to interest much people. It may be for some reason. So maybe it's not really what one should do. For example, the Gaussian process, which one defines here. That's an explicit Gaussian process. It's like Brownian motion. In principle, you know everything about it, but also like Brownian motion, many questions are extremely difficult to answer. But then, is that really interesting? I think so, but probably very hard.
Because in general, so sometimes one lacks tools to prove some equality in distribution in
Yes.
case of stochastic PDs. That is something. So
yes.
It's something. I don't
yes,
know.
But again, if you read the book by Revusior, so it is a very long list of applications of the Ito formula, and then they find a martingale, they take an expectation, and they discover that they can compute an interesting quantity. I would like to do the same, but without the Ito formula, it does not work.
Thank you very much.
I have a question. Maybe the answer is the same, which is in all of your examples, you've taken the linear operator to be the stochastic heat equation. Do your methods work for different linear operators? Yeah,
in principle, yes. But then what changes is mu. So the law of mu will not be the law of the Brownian bridge. So it will be a Gaussian measure, but with a covariance, which is, say, the green function of your linear operator. And then, so I lose some of my power of computing quantities. So you see, so for example, what is the reflecting? So this will be some Gaussian process, but what is the reflecting version of that process? I have no idea. You see, while here, sorry, here this was very relevant. So I wanted, you see. Also, these integration by parts formulae, which I am mentioning, are based on the very explicit computation you can make on the Brownian bridge, on the Brownian processes.
Okay, thank you. It seems I can't see any other questions, so maybe we should take a 5-minute break now, and then we'll start the next talk at 3 o'clock. So again, I'll just invite you once more to unmute yourselves and thank Lorenzo.
Thank you very much.
Stop for 5 minutes, and then we resume with Francesco's talk. Francesco, if you want to share the screen, you can share it.
Can you see? Can you see, Alessandra?
Yes, we can see. Sorry, I wasn't muted.
Alessandro, did you put the slides on Google Drive or shall I do it?
Yeah, I just checking that, okay. In this moment I was checking the link, so I can share the link with the other participants. Anyway, I will recall that I've written the link on the chat. Okay, Francesco, is he here?
Okay.
Okay, maybe it's time, so maybe we can start. I've observed that some people has entered now, so when you start, then I will retype the link to your slides. Okay, because people entering later, they don't see the chat, what was written before, at least in the chat. So it's a pleasure to have here now, the talk of Francesco Caravenna. He will talk about the high-res reconstruction theorem with regularity structures. So please, Francesco.
Okay, thanks a lot, Alessandro and Amanda, for the very kind invitation. It's a pleasure to have the opportunity to give a talk in this seminar. I'm going to talk about Martin Heirer's reconstruction theorem, which, as Lorenzo mentioned, is one of the pillars of his theory of regularity structures. And the content of this talk is is based on a joint work with Lorenzo. Regularity structures has been a major achievement, and it's a very powerful theory to make sense of singular stochastic PDs, and it's a very deep and also difficult theory. And somehow one of the motivations that has led to this paper with Lorenzo is to present an important piece of this theory, the reconstruction theorem, in a way that avoids talking about regularity structures directly, because it can be formulated as just a statement about distributions. So I decided, in order to give some motivation, to start from stochastic analysis, basic stochastic analysis, so integration with respect to Brownian motion, to motivate the very interesting and important Sewing lemma, which Lorenzo alluded to, and which is somehow the precursor of Martin Heirer's reconstruction theorem. And then I will describe the reconstruction theorem and its meaning. And if there is time, we will mention some of the possible applications. Okay, so let's fix two continuous but non-smooth functions. So we call them x, y, and y. They are defined on the unit time interval with values, say, in R. And they can be possibly random, and indeed we have in mind the case when y is a Brownian motion. But for the moment, let's think of them as given trajectories of these processes, so two deterministic functions. And one of the key questions of stochastic analysis is how to give a meaning to the product between x and the derivative of y when y is non-smooth. So we call a small f this product, and somehow the solution of stochastic analysis is try to give a meaning to it, to the integral. So to the integral of x times the derivative of y, we call this integral capital I of t. And if we are able to give a meaning to I of t as a continuous function, then we can define f just as the derivative of I. So this is the key problem somehow in stochastic analysis. And okay, since we know that it's not possible to give a meaning to this integral in interesting cases in a pathwise sense, we would like to understand more precisely where the difficulty is and how to give somehow a robust solution. So let's start with a very elementary approach, and let's try to give a local description to the integral we want to define. And in the smooth case, it's very easy to check that the integral between s and t, when s and t are close, of x times y dot, can be approximated very easily by just pretending that x is constant in the interval st. So we can just replace it by the value it takes on the left side of the interval. And so we get x times the increment of y. And the remainder is small o of the time width. Okay? So we can write that the increment of the integral is given by a very explicit term that we call the germ. In this case, is just x times the increment of y, plus a remainder, which is small o of t minus s. The very good point about this second line is that somehow it's very elementary and does not assume anything about x and y. So if you give me two continuous functions x and y, I define A, the germ, in this way, and I can ask if there is a function, capital I, which solves this equation. Okay, so this is a very elementary problem. And the solution to this problem is known as the Sewing lemma. It's a very elementary result in a sense. So I am given a germ, a continuous function of two variables, a, s, t, and it turns out that this equation has a solution, and it is actually unique. It's always unique, it's very easy to see, but existence is granted if the condition that is written here is satisfied. So this is the condition. Now I'll comment it. The condition is that there must exist a strictly positive gamma, such that if we compute this quantity, this strange quantity, well, this decays as the time difference t minus s to an exponent which is 1 plus gamma, so strictly larger than 1. So what is this expression? It's better to look at the drawing. So we have 3 times s, t, and the middle time u, and we are taking a of the whole interval, and we are subtracting the sum of a over the 2 smaller intervals. So in a sense, asking that this quantity is small is asking that capital A is not so much different from being the increment of a function. You see, if A was an increment, this would be 0, of course, by a telescopic argument. A is not an increment because A, in our case, we are interested in this A. But if it is small enough in this precise sense, then there exists a unique I which solves this equation. Okay, so this is very elementary, this lemma by Gubinelli and Friel and Della Pradelle. And you can really get I very explicitly. And so let's call this condition coherence. So when you have a germ, a function A, which satisfies this, we call it coherent. Okay, and now let's take this germ, the one we started with, and let's compute its coherence. So this increment, it's totally elementary, and the coherence is just the product of the increment of x times the increment of y over the 2 subintervals. Okay, so we have s, u, and t. Okay, now from this it's immediate that we can say something if we assume, we make assumption on x, for instance, and on y. If you assume that x and y are Hölder functions, which means that the increment of x is controlled by the size of the interval to power alpha, and the increment of y is controlled by the size of the interval to the power beta, then we get that overall this is controlled by t minus s to alpha plus beta. So if we remember that we want to get something larger than 1, it's immediate that if we assume now that alpha plus beta is strictly larger than 1, then there is a unique solution to the equation, which means that we can give a canonical, a robust definition of the interval on the integral of x times the derivative of y. Okay, this is very classical, it dates back in a slightly different context with finite variation, with p variation instead of Hölder functions, to a celebrated paper by Young in the 30s. And it shows that if we have Hölder conditions on integrand and integrator, and there is a trade-off, you see, we can make sense of the integral, sorry. So far, so good. And let's now try, of course, to apply this to Brownian motion and to see why it fails. We know that it has to fail because we know that the stochastic, the Ito integral, for instance, cannot be defined piecewise, but it's instructive to see what's the problem, because we know that Brownian motion is indeed a Hölder function, a random Hölder function, and its Hölder exponent is a half minus epsilon for any epsilon, so I would say a 1/2 minus, but not better than that. And then if we apply the Young condition, which is written here, we see that we need to require that alpha is larger than 1/2. So if we want to integrate x against y, and y is Brownian motion, to apply the canonical definition by Young, x must be Hölder of an exponent which is strictly larger than 1/2. This can be done pathwise. However, this rules out most interesting cases. Why? Well, one of the most interesting cases is for sure the case of a stochastic differential equation, one of the main motivations for Brownian motion from the start. So imagine you want to look at this stochastic differential equation. The derivative of x is a function of x, sigma is a smooth function, times the derivative of Brownian motion. Okay. You can look at it in the integral form if you wish, but the point is we cannot apply the Young theory of integral because we cannot expect that x behaves better than b. Just think of the trivial case when sigma is equal to 1. When sigma is equal to 1, as smooth as you wish, a constant, you get x is equal to b. So we cannot hope that x is Hölder with an exponent better than beta, and beta is slightly less than half. So we cannot just make sense of this, which means that the germ, rephrased it differently, this germ, x times the increment of b, which is the approximation of our integral, is not coherent. And now what's the problem? So what's the solution? Well, one solution is stochastic integration. But the message, I mean, I told you this for one important reason, is that the Sewing lemma can be applied. The problem is that this germ is not accurate enough to describe the integral. And the solution is to enrich it. So we can define a new enriched germ. So this is an approximation of the integral of x in dy. So this is the first term we had before. And then there is a way, a natural way to define a second term, x prime of s, which is explicit if you want to solve this equation, times a double integral of Brownian motion, which makes the germ coherent. Now, what's the trick? The trick is that this second term is non-canonical because there is an integral of Brownian motion with respect to Brownian motion, and we know that there are many choices. There is Ito, Stratonovich, and many others. But the key point is that if you fix your favorite choice, then there is a canonical way to define integrals for processes in a class which is large enough to solve this equation. Okay, this is the starting point. Okay, not really the starting point, but this is one of the key points of rough paths, in particular its development with the theory of controlled paths. And somehow the message, this is, okay, I stop here with the stochastic analysis, but the message is we can make sense of ill-posed operations like these products or integral by giving local descriptions, local approximations, which are accurate enough. And the interesting message is that this or these are somehow very explicit. And yeah, this is the idea that led to rough paths and this robust theory of one-dimensional stochastic equation. Okay, so good so far. And now we want to go to higher dimensions, because it's quite clear that everything I told you so far is very one-dimensional. I used the increments property, the arrow of time, if you wish. So we'd like now to go to higher dimensions. So as Lorenzo mentioned, when you look at PDEs, for instance, in higher dimensions, stochastic PDEs, the solutions are going to be often distributions. And so we want to give a version of the Sewing lemma for distributions. This exists, and it is indeed the reconstruction theorem. So the reconstruction theorem is really the extension of the Sewing lemma to higher dimensions and to distributions, also to one dimension. But so now my goal is to try to get there by making analogy with what we have just seen for the Sewing lemma for the one-dimensional case. So remember that in the one-dimensional case, we looked at this equation where we think that AST is a given germ, is a given function of two variables, and you can keep in mind x of s times the increment of y to approximate the integral, and y is the unknown. Okay, it's a continuous function. So in a sense, we have given a local approximation for the unknown, I, capital I, sorry, by assigning a germ A. Now, if I want to understand how can I translate this using distribution, let's take time derivative. So let's define f of t to be the time derivative, the derivative of capital I. Capital I is a continuous function, so it might not be differentiable, but its derivative exists as a distribution. I'll come back in a moment to that. And again, A, I assume that it's a continuous function, so I can take its time derivative in the second variable, and I obtain a second object, fs of t, which is a distribution in t, indexed by s. Okay, so this is an elementary step, if you wish, but it highlights a point that from now on there is no symmetry between s and t, so s is an index and t is a variable which is actually, okay, it denotes the variable of a distribution. And now we can make a very simple thing, just rewrite this equation using our new two objects, small f and capital Fs. The left-hand side is like f integrated on the interval st, so formally you can write like the distribution f evaluated on the indicator function of st. The right-hand side is, again, this distribution fs evaluated on this indicator function, plus a remainder. And somehow this very simple just rephrasing of equation 1 is suggesting how should we proceed with given distribution, because we are looking here and we have a distribution that we have to find, and we have a candidate local approximation for it, and we are testing the two distributions on the same test function, which is for t and s close a very localized one. So this is the thing we want to keep in mind. We'll come back in a moment to that. And so let me first give some basic notation. So let me call D the space of smooth test function compactly supported, and by D prime the space of distributions. Okay, so which is the linear and continuous test functionals on the space of test functions, where continuity, okay, we will not really use it apart in a very specific point. Continuity is required in this sense. We fix any compact set, then we can control the distribution of the test function by the CR norm of the test function for a suitable R, which depends on the compact set. Okay, this is the definition. And now we extend, we call germ any family of distributions indexed by space points. You see, before we called the germ a function of two variables. The germ was AST, but we understood that when we take the derivative in t, we get an object of two indexes which are very different. So a germ is a family of distributions which are indexed by space-time points. And now we can rephrase the problem that we saw in the one-dimensional case, and the problem we want to solve can be loosely stated as follows. Let me fix a germ fx, so it's a family of distributions indexed by space points, and I ask if I can find a single distribution which is locally well approximated by fx, which means that if I look at the distribution close to a point x, this is approximated by the germ fx. Okay, now first, what do I mean by locally well approximated? There is a very standard, if you wish, way, if not canonical, to make sense of this. So let's fix an arbitrary test function phi. We just ask that it has no zero integral. And then, so phi is this one, and then we define its rescaled version, which is just the test function phi, which has been centered at point x and rescaled to be of size lambda. So this is the precise definition, and the only requirement is that the area is preserved, so the integral does not change, which explains why I put 1 over lambda to the d here. Okay. Now, what is the intuition? It's quite simple. Ideally, I would like to evaluate the distribution at a point, but I cannot, so I can just plug in this test function that when lambda is small, is like testing the distribution close to a point x. And then I can define what it means for a distribution f to be approximated by a germ fx, by another distribution. In this sense, I ask that if I take these two objects, I evaluate on the same test function centered at x, and look, x is the same point here. Then when lambda is small, these two objects are close. You see, I only ask that this is equal to this plus something that vanishes when lambda is smaller, and uniformly in compact sets. If you wish, you can put yourself on a compact in space, but so the message is that this is a very natural way to ask that small f is well approximated by capital F. Okay, so this is what we can do. We do actually something slightly different, because instead of asking just small O of 1, which is not very quantitative, we put something a bit more quantitative. So we replace the small O of 1 by the capital O of lambda to the gamma. So we ask that the difference between these two objects vanishes at least as a power of lambda. So we can now rephrase precisely the problem. The problem we want to solve actually. The problem that the reconstruction theorem solves is the following one. Given a germ, capital Fx, which is for the moment just an arbitrary family of distributions indexed by space-time, by space points, we want to find a single global distribution that is locally approximated by the germ, in the sense that the distribution minus the germ at x, when evaluated on a test function at x of small radius, vanishes at least with the radius to some power. And for some arbitrary fixed test function. Okay? Now, there is something good about this problem, is that uniqueness is for free. It's very elementary to show that given an arbitrary germ, capital Fx, there can be at most one distribution which solves this. Because, well, you take the difference of two solutions and then you will see that it must be zero. Existence, on the other hand, is non-trivial, because we already know that in the one-dimensional case, the one that we somehow solved or analyzed with the sewing lemma, we saw that in the one-dimensional case, there was a request which was coherence, which was this one. Now, it doesn't seem to be clear how coherence translates to the new setting. But actually, if we define, say, remember that now we call Fs like the time derivative of AST. Now, this condition translates to the following condition for f. Okay, so let me call S, U, T. Let me call them x, y, and y plus lambda. Then this condition, just an exercise, becomes this condition here. And this condition here, which I will comment in a moment, is what motivates our definition of coherence. Okay, so this is the key definition, the key assumption that we make. So far, the germ was totally arbitrary. And now we define a germ to be gamma coherent, where gamma is a parameter. And okay, I will tell you, but we can even take it real, not only positive, even though the positive case is the most interesting one. If we can find a single test function, an arbitrary one, we just require that it has non-zero integral, such that this condition holds. Okay, so let's look at this condition. What are we doing? We are comparing two elements of the germ, one at x and one at y, and we are testing against the test function localized at one of the 2 points, say y. And then somehow we are requiring that this, when x and y are close and when lambda is small, is sufficiently small. And the precise way to require that is a balance between a power of lambda and another power of the distance between x and y plus lambda, where, attention, alpha is a negative number, a non-positive number. So, okay, the precise definition, since we are on a non-compact space, is to fix a compact set and to require that this condition holds uniformly when x and y are in compact set, when the radius of the test function is between 0 and 1, and we allow this exponent to depend on the compact set. Okay, these are somehow very reasonable and technical comments and assumptions, but somehow the key assumption and the key idea is that we want that when lambda is very small, much smaller, sorry, when x and y are very close and lambda is small, but attention, the point is that when x and y are much closer than lambda, this vanishes. However, the subtle point is that if x and y are fixed and lambda is going to 0, if lambda is going to 0, it means that the test function shrinks to a point. Then we cannot ask this to be small because fx and fy are a distribution, and in general this can well diverge. So you see, if x and y are fixed and we set lambda to 0, we have lambda to the alpha, which, since alpha is allowed to be negative, can as well diverge. So this coherence condition, which is an assumption we make on the germ, which takes some time just to absorb, is a way to require that fx and fy are the two distribution fx and fy are close when x is close to y, but at the same time allows them to be true distributions. So it allows a rate of divergence in lambda. Okay, so you see that if I take x and if x minus y is smaller than lambda, then in the right hand side I get lambda to the gamma, and if gamma is positive, I really have something which vanishes. Okay, so this is the definition of coherence, which is elementary, even though a bit involved. But okay, I'll come back to the moment to this. But this was really motivated by what we saw in the one-dimensional case. And this exponent alpha, the divergence exponent, is allowed to depend on the compact set, but in many cases it does not depend on the compact set. So we can take just one fixed alpha, and then we say that the germ is alpha gamma coherent. Good. And okay, let me make some comments. This I told already many times. So coherence is a way to require that fx and fy are close. So fx is an accurate description of a unique object. And an example which we saw quickly before, if I take a germ in the old sense, that is a continuous function of two variables, which satisfy this condition that I discussed before, then we can take the germ which is the derivative in the second argument of that, and this new germ is -1 gamma coherent. Now this -1 refers to the fact that A is only a continuous function of T. So its derivative is just a genuine distribution. So this -1, this alpha equal -1 is a sign of the fact that we can really deal with distributions. Okay, this is somehow a bit an example, but a general example. But there is another much more elementary example which we all know, and this is the Taylor polynomial. That is, let us now fix a function which is holder of some positive exponent. So this means that actually it has continuous derivatives of all order up to the integer part of gamma, and then it is holder with the difference of gamma and its integer part. Now we can construct its Taylor polynomial of degree, the integer part of, sorry, alpha is supposed to be gamma. Okay, correct. Okay. So, yeah, this is the standard Taylor polynomial. And then it's just a computation, and it's an exercise to show that if you take the polynomial, Taylor polynomial at x and Taylor polynomial at y, now these are functions, so there is really no need to evaluate them on test functions. I can evaluate them on fixed points, and I take a third point z. Then it's an exercise to show that this is bounded by the distance between the base points x and y, and then the distance between the argument and one of the base points raised to the power gamma. Okay? So this is nice in a sense because there is no need to subtract. So it's really a continuity property. And now when you integrate with the test function which has radius lambda, this gives rise to lambda. Okay, now that we have defined the Taylor polynomial, sorry, the coherence, we can finally state the reconstruction theorem. So the reconstruction theorem can be stated as follows. Let's fix a germ which is gamma coherent, okay, for any gamma which is real for the moment. Well, then equation 2, okay, you might as well have forgotten equation 2. Equation 2 is the problem we wanted to solve. The problem of finding a distribution of small f which approximates the germ with a power gamma, with an exponent gamma. Well, this has a solution, but let us write explicitly, spell out the solution. So we can state that there is a distribution such that the following holds. If we fix a compact set, if we fix an arbitrary test function supported in a unit ball, then the function f is approximated by the germ in the sense that if we evaluate them on a test function centered at x of radius lambda, the difference is controlled by a constant times the radius to the power gamma, when gamma is non-zero. And if gamma is 0, it's 1 plus log lambda. So there is a logarithmic correction. So if gamma is negative, this is something which diverges, okay? But still is a control. It cannot diverge worse than that. But if gamma is positive, which is the case we're interested in mostly, then this is positive and this vanishes. So we have a solution, and this is uniform in compact sets and when lambda is also between 0 and 1. Now, what is C? Well, C actually is a constant which depends on the compact set, on the germ, on the test function. But see, it is interesting to see that actually it's controlled by the CR norm of the test function for a suitable power R. Sorry, for a suitable integer R. So, which means that this relation is also uniform in the test function. Because as long as this is bounded, the constant is bounded. So that's okay. And finally, if the exponent gamma is strictly positive, which is the interesting case for us, then in this case, your distribution, the one distribution f that we show the existence of, is unique. So we can define a map, capital R, which is called the reconstruction map. It's also linear on germs. And so we have indeed the existence of a unique distribution which approximates my local descriptions. Okay, so this is the big result which lies somehow behind these regularity structures. One of the part, I'll come back to this in a moment. But let me make some comments. okay, the first comment is that this coherence condition is not only sufficient, but it is also necessary. So it is really optimal. So I'm saying that if you're looking for a function f which fulfills this property, then the assumption that the germ is coherent is both necessary and sufficient. So it's optimal in a sense, in a precise sense. Then the second observation is that when gamma is not positive, then we have no uniqueness, but it's still linear, the map. Okay, this is okay, I will not have time to go into details, but this is based on the fact that the coherent germs form a vector space. So if you have the sum of two coherent germs, still a coherent germ, which is non-obvious since the test function phi in the definition of coherence was arbitrary. And now, yeah, the last point is that when you have a germ, F, you can compute its local homogeneity. What I mean is that you take the germ, you evaluate on a test function centered at x of radius lambda, and when lambda goes to 0, you can show that this can at most diverge polynomially, like a power of lambda, and this beta, which can be negative, it typically is negative if it is a true distribution. It's called the homogeneity of the germ. Why do I talk about this? Just to say that in the reconstruction theorem, there was this uniformity for some exponent r, and this exponent r has to be chosen larger than both the negative homogeneity and the negative alpha, which appears in the condition of coherence. Okay, this is slightly technical, but the point is we have essentially three exponents which characterize the coherence of a germ. Two characterize the coherence, and then we have the homogeneity. Okay. Okay, so yeah, so in this last part, in the last minutes, I'd like now to comment about the role of this reconstruction theorem in regularity structures. I promise that I will not define regularity structures, so I'm not doing that, but I'd like now to make a link with what Lorenzo has talked about. So let's fix a singular PDs, stochastic PD on RD, like the KPZ equation, for instance, or the 543 equation in 2 dimensions or in 3 dimensions. So, and the point is, this has a solution which is which is expected to be a distribution. In regularity structure, what happens is that one associates to the solution that one wants to find a germ in the sense that we have defined, that is, we represent the solution, which in principle is just a fixed distribution, by a coherent germ, by a family of distribution, one for each space-time point. In case you are familiar with the regularity structure, the link is that when you have a model and the model the distribution, then you can apply the model to the model distribution, and then you get a family of concrete distribution, and this is really the germ. And what is the point is that the solution of the PD that we're looking at, that we're looking for, is the reconstruction of the germ. So in a sense, one should view a germ like an enriched version of a function, in the sense that we can, instead of a distribution, sorry, in fact, instead of assigning just a single distribution, we assign a distribution for each space-time points, which is supposed to describe the local property of the unknown distribution. More specifically, the germs which arise in regularity structure have a graded structure. What do I mean? I mean that the germ, I call it F now, at a point X, is typically expressed as a finite sum over, so A is a finite set, is the regularity structure, by some coefficients which depend on the base points and on the level of the set, times a local basis of distribution. So typically what happens is that if one needs to solve a PDE, there are a family for those PDEs that can be attacked and solved with the regularity structure. There is a finite family of relevant distributions which describe the problem, and one looks for the solution of the PDE, so for the germ which is candidate to describe the solution for the PDE, as a linear combination of a fixed basis of distribution. So you should think of it as a small pi as a fixed distribution centered at pi, in a sense. So this is to say that while we are just looking at a single germ, f of x, actually this is not the full story. In regularity structure, there is a richer structure, which is a graded structure. A is a homogeneity parameter, which describes so the homogeneity of the distributions. And this is important because this enriched structure, this graded structure, is really exploited in regularity structure to define what are the problems of the theory, that is the non-linear operation. So as Lorenzo said, that we want to perform a non-linear operation with distributions, and one way to do it is to use germs. Why so? Well, think of it like the Taylor polynomial of a function. If you have a function which is C3 halves, okay, C1.5, so it's only C1, and then as an extra half Hölder regularity. Well, its Taylor polynomial is a C-infinity function. So you can, okay, I don't go into detail, but you can imagine that in order to define some operations which are problematic on functions and on distribution, using germs to describe these functions or distribution can be very helpful, because a germ can be as regular as you wish, but has the flexibility of depending on the time of the space-time points. So for any point, you can choose. You can imagine that you have a regular version of the object you want to ultimately build. And okay, let me mention that this is not the sole story, also because besides the graded structures and the products, another key element are what is called the Schauder estimates. So this is another important element of regularity structure. And yeah, to conclude, the coherence condition, which yeah, we want to evaluate this difference at x minus fy on a test function. And we want to show that ultimately is bounded by an object of this form. But for those who are more familiar with regularity structure, will recognize that what one actually sees in regularity structure is this expression, which is in a sense more complicated, but also a bit more transparent in a sense, because typically the germs in regularity structure are such that when you evaluate, when you compare two germs at nearby points, the difference when tested on a test function is a sum of terms where you have two counterbalancing effects. On the one hand, you have the distance to a positive exponent, because alpha is typically larger, smaller than gamma. And on the other hand, you have this lambda to the a, sorry, not alpha, a, where a can be negative. So in a sense, you have this strange sum where when x and y are close, much closer than lambda, you have something small. But if lambda is much smaller than the difference between x and y, this can diverge. And the only message I want to say is that to prove the reconstruction theorem, you don't need this. You only need this consequence of that. So if you have this, it's easy to see that if you set alpha to be the minimum value of A, then you have this bound. And this bound is what is enough to prove the reconstruction theorem. And this is why the coherence condition, which only asks for that, is optimal. Okay, let me say this was already present in the technical lemmas in Martin Heirer's original paper. So this is not something new. Okay, so to conclude, I tried to convey the idea that germs intended as family of distribution can be flexible objects which arise naturally when you want to describe singular PDs, and somehow to make the link between germs and concrete distribution, you need the reconstruction theorem, which tells you that if you have a germ which is precise enough, accurate enough, in the sense that it is coherent for some positive gamma, then it identifies a unique distribution. Okay, I think I can stop here. Thank you, Mike. Thank you very much.
Thanks. So now, thanks a lot, Francesco. Now I will ask all the participants to unmute so that we can all together thank everyone. We have some time for questions. You can type the questions on the chat or ask them directly. Yes, somebody? Okay.
Can you comment a bit on Schauder estimates?
Yeah, okay. Yeah, Schauder estimates, okay. Yeah. In general, Schauder estimates is an estimate of the form if I have a distribution in C alpha, and then I have a kernel k, x, y, which decay 1x minus y to d, okay, okay, some exponent, okay, don't, I will, get me wrong, I will be wrong to do it right now. Then when you take the convolution between k and f, this is Hölder of something better, so alpha plus rho, okay, here there is rho somehow. So Schauder estimates is a key tool when analyzing these parabolic PDs, for instance, which tells you that this is in the context of distribution. So if I have a distribution which is Hölder of exponent alpha, and I convolve with a kernel which diverges but not too much, then I improve its distribution, its regularity. The point is that there is a version of these estimates in the context of germs and in the context of regularity structures, because the delicate point is that convolution is not a local operation. So a germ is supposed to describe your objects locally, so it's not obvious now given, so the point is now given a germ, f of x, I would like somehow, so if this is coherent, this corresponds to a unique true distribution. And now I would like to define like an operator of the germ x, which gives me, which gives a new germ, say f tilde x, such that the reconstruction, the reconstruction map commutes with this operation. So you would like to lift the convolution which happens with distributions to the space of germs. And this is possible. This is possible, and it's one of the most delicate and technical points in the theory of regularity structures.
Thank you.
Okay, thanks for the question. So we have a question from Leandro Chiarini.
Hi, I don't know if you can hear me properly.
Yeah, can hear you.
Yeah, okay, so I actually have a few questions. First, just because I don't know if I missed it, do you recover the smoothness as well with your reconstruction theorem?
Recover?
Do you recover smoothness, like Bezoff smoothness as well? With does your your reconstruction? Ah, yeah, it does.
Ah, yeah,
the right space.
yes, okay, yes, okay. I didn't state it, but somehow, if your germ is coherent, say gamma, okay, is coherent, and it has homogeneities beta, say a fixed homogeneity, then its reconstruction belongs to C beta.
Right.
Yeah. So you have if you have a germ which is locally behaves like a Hölder function, the reconstruction will be Hölder with all the distribution. The reconstruction will also be Hölder with the same exponent.
Right. Sorry, I don't know if I can ask more than one question, but I was just wondering if first you are the proof is also based. The proof is based on wavelets as well, like the.
No, yeah. This okay. There are many things that I didn't say. This is an important one. One of the motivations for this proof is that it avoids wavelets.
Okay.
It avoids the wavelets, and it's based. Okay, this I should have stressed. In the coherence condition, the function is arbitrary. Okay.
Yes, that was very impressive, actually.
Actually,
you managed to.
Okay. So in the coherence condition, you see the function is arbitrary. Okay. Mm-hmm. And I think, I have an extra slide which answers somehow this question. I think, yes, here it is. Okay. As a corollary of our approach, somehow we can show that the standard definition of negative Hölder space is insensitive to the choice of test function. So it is well known that usually you ask that a distribution is negative Hölder when you have this bound uniformly for test functions with some bounded CR norm. And it's known that it's enough to ask this for the wavelets basis, for instance, but actually we show that it's enough to ask this condition for a single arbitrary test function. If you have it, then you can recover for arbitrary test functions as well. So it's more of pedagogical value in a sense, but it's nice because it really shows that it's immaterial which test functions you take. You get always the same result. Yeah, indeed, the technique is close in spirit in a sense to what also is the original proof. We define a sequence of approximations using this test function. Mm-hmm. It's different from the wavelet approximation because it will not work. We don't have the wavelet property. There are some other tricks to make it work, but it's quite explicit.
Okay, and promise this is the last question. Finally, so because sorry, I didn't see your proof. Can you replicate this kind of result for other Bezold spaces like PQ? Or is it expected? I know it might be tricky to say.
I think that it is expected, and I think Lorenzo can answer better than me, because if I am not wrong, he might have a couple of students working on this.
Yes, I confirm.
Okay, let me also mention that the approach is quite flexible, and it has been extended to manifolds by two PhD students from Pavia, two mathematical physics students that have been working. The same approach works on smooth manifolds because it's very local in nature. So it's
Okay, thank you very much.
You're welcome.
Thanks for the question. So we have Oleg Butkowski.
Hello. Can you hear me?
Yes.
Perfect. So I just have a quick question. I was trying to think of possible examples of how you apply this reconstruction theorem, which you showed us in slide 4. So could you please repeat again? So let's say in case of the Taylor expansion, so if f is, I don't know, a C gamma function, so what exactly is fx and why, how exactly you are verifying your condition? So could you please?
I see. Okay, so in the Taylor case, you mean?
Yes.
Okay.
The most simple case, I don't know.
Yeah.
Let's say gamma is between 0 and 1 even.
Okay. Then, when gamma is between 0 and 1, then there is nothing to prove, in the sense that then if gamma is between 0 and 1, then you should take the zeroth polynomial, which is just the value of the function at the point x, minus the value of the function at the point y. And if it's Hölder gamma, this is x minus y to the power gamma, which is this one. Okay? So perhaps I can, let me...
No, actually, Francesco, you have to compute fx of dot. So fx of dot is f of z minus f of x. So that's z.
No, fx of dot is a constant in the 0 case. So it's f of x. I think.
Yeah, maybe you're right, yes.
Okay, let me just make this. Okay. Okay, so I'm saying that, for instance, if okay, let's make it in a more so let's say that f is in C, yeah, gamma, and the gamma is between 1 and 2. Then fx is the Taylor polynomial of order 1, so is f of x plus f prime of x z minus x. And then if we compute fx minus fy, so the difference between two Taylor polynomials evaluated at the same point, so two different base points, it is f of x minus, this is very dangerous doing computation directly, it's okay, and then what is that? So it's yeah, it should be plus f prime of x, yeah, z minus x minus f prime of y, z minus y. And okay, I don't go forward, but the yeah, if okay, if I didn't make some mistake here, is the fact is all this is less than, say, x minus y plus y minus z to the power yeah, gamma. And gamma is between 1 and 2, so it's a non-trivial statement because it's decaying faster than linearly, so there is cancellations. So it's really, I mean, it's a computation, it's a half-page computation by just binomial theorem and Newton's binomial, but it's a fact in a sense. If you wish, okay, but I think I don't want to go over time. I mean, in a sense, the Taylor polynomial, I mean, if you start with a function f, which is C gamma, which is gamma with gamma positive, its Taylor polynomial is a germ, but you already know the reconstruction of the germ. It's the function f itself. So why should you bother? And actually, you might be interested because, okay, I can say just something very quick. If you have a distribution in C alpha and G in C beta, and beta is negative, then one of, again, this is the analog of the Young integral, so the Young product, if you wish. If alpha is positive and the sum, and it's larger than minus beta, okay, then there is a canonical definition of the product. Okay, and one way to define this is to consider the germ, which is this one, fx times g, where fx is Taylor polynomial of fx. This is well defined because it's C infinity, so you can make a product, and you can prove it, and that this is coherent. Is alpha plus beta coherent? It's a computation. It's done in our paper, and it's also in Martin Heira's original article. And then, since it's Taylor, it's a coherent, there is a unique distribution which is approximated by that. So you might be interested, even if you know the reconstruction, you just to give a very accurate local description of your object.
Thank you.
Okay, thanks. Is there any other question? So if not, I think it's also time to stop. So I ask to participants to unmute themselves so we can thank both the speakers of today.
Thank you very much. Thank you.
I recall you that next week we will have Cristina Toninelli and Fabio Martinelli. So have a nice evening or a nice day. See you.
Thank you. Thank you very much for the organization.
Okay. Grazie, adesso vi parlo in italiano. No, perché ho avuto una giornata. Adesso innanzitutto un attimo che sto un po'